Great. Yeah, I think if everyone is, if most people are here, maybe we can get started. So, yeah, hi everyone. Thanks for coming. So, Yushen has been with us now. Is it 2 years, Yushen, or?
I think I'm a second year DS PhD, but technically a third year graduate student.
Right, because you were here for 1 year for your master's as well.
Yeah,
And then previously you were at RPI.
yeah,
So Yushen is it's just good to hear your talk. So
yeah,
definitely.
sounds good. Yeah, so let me share my screen and then we can get started. So hey, guys, I'm Yushen, and today I'm going to present the multi-step extension approximate implicit method. I think I also briefly mentioned this project in the IACS research day in April. Yeah, so if you guys are here last time, then yeah, it's a more longer version of it. Yeah. So a brief introduction is about this continuous time optimization. So for optimization, we are interested in finding the optimal solution of an objective function f of x. And so finding the optimization of this function is actually equivalent to finding the stationary point of a differential equation, usually that's the first order differential equation. And several examples are if the function g is a gradient system, then it will be equivalent to stationary point. There's also other system like rescale gradient system, which the stationary point um, also equivalent to finding the minimum of the objective function. And also we have to point out what's the definition of stationary point, which is basically the limits of x of t as t goes to infinity. So we actually need to talk about this. So for us, we are interested in this gradient system. And for this gradient system, the first thing is that we have to talk about the existing uniqueness of the system, right? First, it's hard to calculate analytic solution analytically. So you cannot just find the solution and tell me that the existence exists. You actually need to use generally more mathematical technique to deal with the existing uniqueness of it. Right? So analytic solution may not be easy to compute. And the point is that if the function is L smooth, then the solution of this gradient system will be exist and unique. And also this is for global like existing uniqueness, which is special from normal differential equation system. Normal differential equation theory will you only have local existing uniqueness. And there are also some relative work talking about how do we use continuous time optimization in like optimization world. Yeah, so there's several paper talking about that. And after talking about the discretization of the continuous time system, then as you mentioned before, the analytical solution is hard to compute. So we actually need to discretize it. And if you are taking about basic numerical analysis class, then you will see this the easiest numerical approach, which is just by this order scheme. And for this, in order to connect to optimization point of view, which is basically if you do the discretization for this gradient system using forward order scheme, then you actually get the gradient descent methods, which is another way to interpret the order scheme in optimization point of view. And there are certainly some benefit of this explicit method. The first thing is this is easy to compute, but if you learn about this numerical analysis class, you may know like, oh, it actually needs, for explicit method, it actually has very strict requirement for the stability issue. And there's also an alternate approach to handle this using this differential equation, which is by implicit method. And the implicit method, which means that the update depends on the current iterate. And also another very classical example about this is this backward order scheme, which is also, if you have taken numerical analysis class, then you definitely will see this kind of updates like in the first several lecture of it. And also in optimization point of view, the backward order scheme can actually be understood as a proximal point update over here, which is actually a very classical optimization methods. And so that these two are actually equivalent. And usually this exact update, because it's an implicit update, so you actually have to solve this, solve another system of equation, which you cannot do it usually, you cannot do it analytically. So you actually have to solve it by other numerical methods, like Newton method, something like that. But you got good trade-off, which you have less strict requirement for stability. And then we just, and the other thing that we need to talk about for this numerical word is this truncation error stability and convergence spec. And the truncation error is usually something which is defined as the following, which is just when you plug in this true solution into the update form for the discrete solution, you'll get the truncation error. And truncation error usually means consistency in numerical area. And for example, if you consider the Euler scheme, then you just plug in this value into it, and then you will get this truncation. It's usually a first order truncation error. And the consistent, which means that this truncation error will converge to 0 as alpha tends to 0. And also the order is tau when epsilon alpha is alpha to the tau power. And the other important concept is about the stability thing. Well, if the solution, usually the stability, there are many kinds of stability definition in the word, in numerical area, like A stability, something like that. But usually a way of saying stability just say that your numerical scheme will not diverge. So it might not converge, but you guarantee that it is bounded, so that you won't have a solution, very ill-conditioned solution. And the example is that the follow order scheme is stable when it is between alpha and 2 over L, where L is the L smooth when the function is L smooth. And in general, I think lacks equivalent theorem, or there's other general theorem saying that consistency plus stability imply the convergence.
So Yushen, I wonder if I can ask a question. So you sort of discussed a lot of these really nice properties about continuous trajectories and discretization. And I think you're sort of alluding to, but can you just tell us concretely, what does this mean for optimization? What does this mean for if you're planning to use a gradient descent algorithm? What does this mean that you have to be aware of?
Yeah, so I think the stability actually plays some role in optimization world, right? Because if you want some inspire optimization method based on this numerical update, then the stability tell you that you won't diverge, which is, although it doesn't tell you that you converge to the solution, but doesn't diverge also help you to prove your convergence result, right? And also help you in some point of view. And for the truncation error, because in optimization world, we usually do not shrink alpha to 0. So usually, the truncation error doesn't play too much role. But there is still something useful over here, which when you analyze this truncation error, like when we go back to here, like this error will depends on alpha, right? But there is some kind of other constant coefficient on the other side of the alpha. Although the alpha does not shrink to 0, but the bound on the other side of the alpha, like you have times on like derivative of some function, like some other constant c might play some role when you analyze the convergence rate of it. That's how I integrate this in the optimization words.
Yeah, and I think it's also interesting to note, right? Even if alpha doesn't go to 0, you are going to get to your stationary point.
Yes. Yeah, the point is that the alpha doesn't play some role, but the arrow like alpha times some constant, and that alpha times some other coefficient, and the other coefficient actually plays some role for this optimization analysis, because the other side will still tend to 0 as you iterate more. That's how this like truncation error tell you, not the alpha, but the other coefficient, which is kind of interesting. It's
Right.
also explain why the optimization method doesn't speed out even you try higher order scheme, because the alpha is fixed. So you don't really get like the linear, like this convergence rate as the optimization method, because the alpha doesn't shrink. But the other coefficient of the bound does play some role over here.
And do you also want to touch lightly on what is the, when you say the truncation error converges, what do you like, what does that mean for optimization?
So the truncation error, yes. So it's basically mean that you want to compute whether a point converges to, whether a discretized point converges to a stationary. Let's see if I can write something over here. Oops. Let's see. Let's see if I can try to write something over here.
I guess the point I'm trying to get at is
Yeah.
there's two notions of convergence, right? There's the convergence in your truncation error, but there's also the convergence in optimization.
Yes, because the convergence of truncation is about whether the true solution converges to the approximate solution. But for optimization view, the convergence reference whether your solution converges to the stationary point.
Right, and one does not imply the other necessarily.
Yeah, but I think I'm trying to find out that we can use this truncation error analysis to prove the convergence of stationary points by considering. So for optimization words, you want this. So if this is the stationary point, you want this convert to 0. And for the optimization point of view, for the numerical point of view, you want alpha times, like alpha times k. Like this is the true value of the function x. You want this convert to 0 as alpha to the infinity. And so how this can help to prove some result for this? The point is that you can rewrite this term as xk plus 1 minus this x alpha k plus 1. And plus x x star plus x, this alpha k plus 1 minus x star. And then for this continuous, so this is the as alpha goes to 0, which means this is the limit as t goes to infinity of x of t. So this is basically the arrow created by the continuous flow. And this is the arrow. Well, it doesn't convert to 0 by fixing alpha. But if you try to let k tend to infinity, so this is, and then this term can actually convert to 0 too, which is something that we want, that is quite interesting. And as mentioned before, this is a truncation arrow, and this is some arrow alpha times something. Although alpha is fixed, but this term can convert to 0 when you iterate over k, like larger and larger.
Yeah, it's an interesting way of, changing the two problems. Yeah. Okay, I'll stop now.
Yeah, yeah. And yeah, and then so go back to talking about the stability things, and so usually stability is usually connected to the conditional of the function f, and when the function is mu strongly convex and L smooth, then this condition is usually defined as um, the largest eigenvalue of the Hessian matrix of fx divided the smallest eigenvalue of of the Hessian matrix of f over all the y or over all the y. Usually, if you have larger L, which means that you have smaller step size, and if you have smaller mu, usually mean you have slower decrease in f of x case. And usually, the back conditioning will lead to convergence very slow and has very small step size. And in machine learning problem, like condition is actually a very large issue in machine learning problem, and usually need to decrease step size to usually you have to slow down the step size, which will slow down the convergence. Because if you increase the step size, you will have some issue of divergence issue. And then there are existing solutions such as this momentum-based method or adaptive-based method, which can somehow handle this issue, but not completely. And for us, we invested this approximate implicit update to deal with this conditional issue. And then now we talk about this backward differential formula. So basically the backward differential formula is just a special kind of multi-step methods. But the multi-step only do on the x side, but not on this right-hand side. So basically for general multi-step method, you have this multi-step method. So you will have a linear combination of this gradient of the previous step. But for optimization point of view, we do not want to add more time step over here, add more like gradient call over here because it will increase a lot of computation issue. So instead, we will prefer to add more time step over this x iterates because because the pass value of x is already computed, so you don't have to recompute it. So you don't have to worry about computing this previous iterate again. So that's the reason why we only have this have the x update over here, but not the gradient f over here.
Yeah.
And then how to choose the value of c is basically choosing c so that to minimize the truncation error. And yeah, so although we mentioned that like truncation error doesn't speed out the convergence rate, but it does speed out the convergence numerically, which we will show later. And then so a little bit pointing out how this BDF update is similar to the one-step proximal point method, which is basically everything is almost the same except we change this x of k to tilde x of k. Yeah. And the tilde x of k is just a linear combination of the previous iterate. And then CI is chosen based on this maximizing truncation error. But as mentioned before, finding this, we either solve the equation here or like, which is equivalent to find the minimum of this is actually hard. So usually you cannot solve it analytically, but you have to solve it like numerically. And then just talking about a brief projective example, which is minimize where the objective function is a projective function. And then you just use m iteration of gradient descent to find the minimum of this function. Basically, the update is doing like this, where you just do some calculus and then do the update over here. And then the rate of convergence can be computed as the following. So this is basically the radius of convergence. And So the left-hand side is the figure that we fix the matrix. So we fix the matrix M, and then iterate to change the number of inner iterates. So as mentioned here, we use M iteration of gradient descent to find the minimum of this inner update. And for the left-hand side of the figure, we just change different value of M, which is from 2, 8, and 100 to see how the radius of convergence changes. And for the right-hand side of the figure, we just basically will try different matrix M with different maximum eigenvalue, which is this L, and see how it changes. And we see that the BDF2 actually, for all this kind of different settings, usually BDF2 perform better than BDF1 and have better convergence rate than BDF2 and better radius than the BDF3. And the other application is talking about this matrix factorization, which is finding the minimum of this function where U and V are two matrices. And the point is, and this problem is actually very yield condition non-convex problem. And usually a good approach of doing that is doing this alternating descent, which is just when you initialize with two value U and V, and then you first fix V as this initial value, and then try to find the minimum of U by fixing this V, which is basically a least square problem. And then after you get the update of U, and then you fix the value of U, and then find the minimum with respect to V over here. And usually this will provide very good results. And for our approach, we try to calculate this implicit update by using this alternating approach, which is doing the following. And this also saying this issue also has several good point, which is the first thing is that you can do this in parallel so that you actually got faster speed. And the other thing is that, like in this case, where you can calculate this arc mean analytically, but in some more complex function when you cannot calculate this arc mean analytically, by then this is like when you split the variable to different sub variable, then you can try try other methods like Newton method to find the minimization, which is hard if you find this minimum in general, because usually if you have larger dimension, well, you use Newton method, and then you will have to compute the inverse matrix in very long time. But when you try this alternating approach, in this case, then because each variable, you can split the variable to different sub variables, so the sub variable has less dimension. So the iterate for using this Newton update will be easier. And then we also try to numerical experiment where we try different number of inner iteration, and then we notice we'll see that the higher BDF scheme actually benefit in the following example. And the last example that I'll talk about is this simple binary classification text over this Q layer neural network. And here actually Q is 7 over here. And then this is basically circle where you have this is basically where you have like a circle which classify the point, and the inside of the circle is 1, and outside of the circle is -1. And then we'll try to train the neural network to find like the splitting, like this area to split in these two regions. And then this is several numerical experiment we have done. And the left top figure is the gradient descent comparing to the Ron-Kuta 4 update, which is another numerical method. And for the right top side is a gradient descent comparing to this proximal point method. And the left side down figure is the BDF method, which compared to the gradient descent method. And the right downside is the gradient descent compared to the BDAF3 methods. And then we do this experiment over 10 starting point. And then the shading region is just it's just all the shading region is just all the accuracy over this 10 trial. And then the top side is the maximum accuracy among all the 10 trial. And the downside of this shading area is the minimum accuracy among the 10 trial. And then the solid line is the average accuracy among all the 10 trial. Yeah. And then some convergence guarantee. So yeah, so actually talking about those kind of experiments, and then we also have some theoretical contribution of those methods. And then the first thing is that we need some kind of convergence result, some kind of assumption for the objective function. The first thing is that the objective function should satisfy this mu convex constraints. And then mu can be positive, negative, of 0. So when mu is larger than 0, the function is strongly convex. And when mu is 0, the function is convex. And when mu is smaller than 0, the function is weakly convex. And L smooth will imply this mu equal negative L convex. So the first thing is for the convergence result for the exact implicit updates. So assume that f is a mu convex and differential area function. And when mu larger than 0, it will converge linearly with rate 1 divided by 1 plus alpha mu. And when tau equals 0, the rates will reduce to proximal point methods. And then when the function is convex, then the convergence rate will not be linear. Instead, it will be sublinear, which will have the following convergence rate. But notice that there is no upper bound constraint for alpha because implicit methods are unconditional stable. And when tau equal 1, the rate will reduce to proximal point methods. And for general mu smaller than 0, the BDF will have the following. So for mu smaller than 0, which means that you somehow one side L smooth, and then you will also have sublinear convergence rate, but you will have some restriction on alpha because the function f is not convex anymore. And also when tau equal 1, the rate will reduce to proximal point methods. Yeah, so the convergence result for the exact update. The good thing is that the BDF has comparable convergence rate as proximal point and gradient descent method. However, it does not show faster convergence rate when tau is larger. This is as we discussed with Yifan before about, although it has faster in numerical point of view because shrink alpha will give you some benefit, but doesn't improve the convergence rate in optimization point of view because we have different goal. And the convergence result are for general choice of C. And for the stability issue, as tau increase, the method will be less stable and require more constraint on the step side when the function is non-convex. And that's the reason why we only talk about the first BDF scheme, because I think after 6th order BDF, it actually doesn't stable anymore. And there's also some issue like exact implicit update is not practical at all. So it will lead us to consider these inexact update results. So for the inexact implicit update result, we will require this gamma contracted result, which is basically the difference between the approximate solution of that update between the approximate solution and the exact solution is smaller than the exact solution minus this linear combination of the previous time step, previous iterates. And then the example of that is that you try M gradient descent for this implicit, try M gradient descent to approximate this minimum function will guarantee you gamma contracted. And also this is the convergence result for the inexact update. So assume that the function is L smooth and mu convex, then and the function and the method for solving this approximate update is gamma contracted, then we will have linear convergence rate when mu is larger than 0. And similarly for the convex function, when mu is 0, you will have the sublinear convergence rate, but there is still no upper bound constraint on alpha. So it's same rate as the exact implicit update. And when mu is smaller than 0, you will also have this sublinear update, but with step size restriction alpha. I also want to point out that I have discussed with Ivan about that how to use truncation error to show convergence result for this. Also, like try to use like the truncation error to show the convergence result. I'm actually thinking about whether we can conduct a more intuitive approach to do similar analysis than what I've done here, so that the analysis will be more intuitive and may contribute to this, and then show that like how numerical methods can improve can do something in the optimization work. And in conclusion, that we investigate the multi-step implicit discretization for gradient flow and boundary condition optimization problems. We also look at exact and inexact combination and compute some convergence result. And we point out that fast convergence in numerical ODE doesn't imply faster optimization, but as we discussed, the convergence analysis in numerical ODE can potentially help optimization, can potentially help to show some convergence result in optimization, and it's more intuitive. And however, in specific instance like this matrix factorization neural network calculation, the BDF does enhance numerical performance. We actually also have tried down some other experiment like compressed sensing over L1 node, like when we consider doing some proximal, when we try to do some non-smooth minimization, we also do see BDF has better convergence rates over there. So I think there are even more practical example that BDF scheme can benefit. So I think that's pretty much the presentation. Thanks. Thank you.
Thank you. Yushen, since everyone seems to be shy, can I jump in with a couple of questions?
Yeah, sure. Yeah.
Brilliant, great. So I don't know, maybe it was slide 10 or something. You were analyzing, minimizing the truncation error. I think you had a, where was it? There on
over here.
Oops. Yeah, there we go. You've got the truncation error, great. And then, which is really great because a lot of numerical analysis kind of skips over the fact we're working in finite precision. And so can we, maybe on the next slide or two, we just pop forward a little. Next one. Keep going. Oh yeah, here. So basically, you're choosing these chi's to minimize the truncation error.
Yeah, I think minimize the order of truncation error.
So it's basically okay.
Yeah. So yes, just because minimizing truncation errors, it's probably not a good word of saying that.
Okay.
Yeah.
So it's the approximation order rather than the truncation error.
Yeah, it's like the approximation order, like asymptotic order. Yeah, so minimize the asymptotic order of the truncation error.
Okay.
Yes. So, but I think as I discussed with Ifan just like in the conversation, we're thinking about so the truncation error, like we discussed here, like people only usually in numerical they're only concerned about this order of accuracy in numeric, like usually in numerical word, like they're only concerned about this alpha to the tau. They usually do not consider the constant, right? There is, because this is some constant times alpha to the tau. And also the constant may depends a lot of stuff. And the point is that in numerical world, people just shrink alpha so that the error will shrink. But for optimization point of view, if you shrink alpha, you actually need more iteration to go to infinity. So there's no point to shrink the alpha.
Okay.
So now we probably, so this is fixed. So we actually need to look at here.
Right.
And this C actually, usually it's like this derivative, like the fourth derivative of this function f, something like over delta t times k, something like that.
Interesting. I was actually misinterpreting this slide then, because I was looking at this thinking that truncation error is basically like trying to compute a numerical derivative using a simple forward difference formula, and that has inherent problems in, well, finite precision arithmetic, and then higher order formulas don't necessarily save you. So what happens in like if you're trying to compute in single precision or half precision? Do you have enough bits to use these high order methods?
I think no. Yeah, can you actually explain a little bit more about things?
Well, so in numerical, you're computing in finite precision, right? You've only got in double precision 64 bits and single precision 32 and so on. And so if alpha is small, you want to talk about the limit alpha goes to 0. But as alpha goes to 0 in finite precision arithmetic, you lose significant digits.
Yes.
Right. So, okay. So I was my misinterpretation. And then on slide 14, your matrix factorization problem. This is very interesting. And so obviously there's lots of algorithms for computing factorizations like this. Why under what circumstances would an algorithm like this appeal to somebody?
Oh, do you mean like this kind of
iterative approach to trying to the alternating least squares algorithm isn't necessarily the most efficient, but why might somebody think about using it?
Oh, this is because people want parallelism. So so the point is that you want to do parallelism during updates. It's like coordinate descent. If you have a function like f x1, if I can dig into more detail about this. For example, if you want to find the minimum of a function like n variable, and then like what you can do, you can try to like initialize some value, right? X, like initial value, and then you just minimize respect to x1 by fixing x2 to xn. And then you minimize respect to x1. And then you will get a arc x1 depend on x2 to xn, like your initial some value. And after you find this x1, now you try to do x2, right? You have x1, and then you do x2. And then you can minimize x2 based on the new value of x1 to x1, x3, xn, minimize it. And then do x3. And then this is like a normal alternating approach to find like minimization of a function f, like just doing this iterative, like doing the alternating minimization. But this approach has an issue, which because in this approach, you have to wait until x1, do the update, and then do x2. But you can do it in more smartly where you initialize, like you don't have to wait until the new x1 update come out. You can just use the previous x1 value to do the update, similar for x3 to xn. And then after all of them, do one iteration and then synchronize it, and then do another parallel update. And this approach, because you only minimize respect to one variable, so usually the first thing is that you can do them in parallel. The second thing is that for each minimization, you only minimize respect to one variable. So this is actually faster, right, than trying to do normal minimizing approach over all the variables.
Maybe Yushen, you can also touch on what is M typically for this method? Like does M need to be very large for this algorithm?
Actually, you don't have to. Usually only for this matrix factorization, it's actually pretty fast. Like 5 or 10 iteration just work.
Yeah, I think even M equals 1 will work.
Yeah, M equals 1 usually works quite well. Usually probably have to do 1, 2 or more steps.
Yeah, so
and this,
I was going to ask, so if you were to compare this with the matrix factorization method, what would you say is the computational difference, complexity difference?
Do you mean comparing to?
Yeah, like this method, let's say we do choose m equals 1, how would that compare to like a matrix factorization method? Like the vanilla one.
Do you mean the vanilla one, just doing alternating one, or?
Yeah, yeah.
I think it's quite
Yeah, I think so.
Yeah, it's quite similar.
Yeah, except for line 2 and a little extra regularization, right?
Yes, that's the point.
Yeah. So that's a big thing. It's not that it's better, it's that it has no difference in per iteration complexity, but it's faster in the number of iterations.
Okay. That's helpful. Thank you.
But maybe also you can touch on some of the newer problems we looked at, because actually what happened with this paper, right? We had great theory, but our experiments were kind of subpar. And then we tried a whole bunch of crazy problems that you would never think to do gradient descent on. And those problems we tended to do very well, right?
Yeah.
Like, I don't know if you want to expand a little more on that to sort of say like where the real, like, because I think actually the point you made about how we should redo our proofs in terms of the trajectory convergence plus the truncation error is interesting, but it's there's always one caveat, which is what if the trajectory is not that fast to begin with?
Yes. But usually you won't get faster than the trajectory itself.
Yeah, so for example, in gradient descent, the trajectory rate is the same as the method rate. So that's so really the only thing we play around with these implicit steps is to take bigger step sizes. We don't actually get to play around with the big O too much, because the gradient flow itself is not that fast. But in these crazy problems we've been looking at recently, it's possible that the trajectory it's faster, right? And so in that case, the truncation error becomes the bottleneck. If the truncation error is the bottleneck, then
So
these methods become, yeah.
I think your discussion about the trajectory is very interesting. I mean, I think I'm trying to think now of methods that change the trajectory, and something like conjugate gradient comes into mind.
Yeah, conjugate gradient is interesting, but it's hard to interpret conjugate gradient in terms of a trajectory flow, because it's not like, if you think about it, the number of iterations is basically the number of variables, right? You kind of take one pass through. So it's not really like it's not in that sense like the iterative method, the way a gradient descent is kind of an iterative method.
Interesting. Because I always think of it, the gradient descent as somehow you're bouncing down the valley, whereas conjugate gradient is trying to take somehow a more intelligent approach. But I still think of it as a dynamical process. So it's interesting that you've got this perspective that
yeah, because it's right, it's always taking these conjugate directions, but like, okay, I'm only thinking of quadratic problems. In the quadratic problems, you basically just take one per the size.
Right. In this simple quadratic problem, you just basically looping through the unique variables in the Hessian, right?
Right. I guess, right. So for a convex but not quadratic problem, it could be also interpreted in this way.
Okay.
But actually, I think the valley problem is a nice. So I think maybe this was one thing Yushen that was trying to explain with the equations, but I'm not sure if the equations is making sense a lot. So if you have this valley, right? So the issue we're dealing with is that gradient descent does this, right? Exactly as you were saying, it bounces around. And if you kind of stare and squint at this is kind of like this is the flow and this is the method, right? So the bouncing around is exactly the discretization error. And it's sort of attributed to, like, if you have a very, very narrow valley, that is a very ill-conditioned problem. And very ill-conditioned problems is where no matter what you do, you're going to be slow. And so the question really, the initial driving question here was really, if we can overcome discretization error without actually increasing any other complexity except this kind of adding thing, right? Would we suddenly develop a faster method? And unfortunately, the answer was no for smooth problems, but possibly for these new problems we're looking at, which includes this one, this matrix factorization. We were really surprised to see how well it worked, actually.
What was the condition number of the matrices you were trying to do?
So
I think so. For me, I'm just trying random matrix R.
Random matrices. Random matrices, sadly, I've been working a lot with Hyeji, one of your colleagues from AMS, and we were using lots of random matrices as test cases, and they're really, really interesting, but they're very depressingly boring because they converge so rapidly to the average case.
Oh yeah, that's
And they're usually very well conditioned, right? They might have some small eigenvalues near zero, but most of the eigenvalues are very similar, depending on the underlying generator. Yeah.
So I think the Hessian for this is not R. I think you're right that R is like if the Hessian is random, it's very boring. But the Hessian of this, you said the Hessian of this is Gaussian, right? Sorry, the R is Gaussian, but the Hessian is not R.
The
So
R
I think
is good.
Yeah, R is a Gaussian random matrix.
Okay.
I think the Hessian is actually, it must be, otherwise why else would it work so well?
Well, that's what I'm. It works so well. So what I guess what I'm saying is it would work well if lots of if you don't have that steep value problem, right? So most of the eigenvalues are going to be clustered towards one-ish, and you get they're spread across the unit disk, right, in the complex plane, but just because of the surface area, there's going to be a whole load that are sitting on the edge of that circle. And so it would actually do a great job on those probably. So yeah, try something that, as you said, gives you a whole load of different eigenvalues in the spectrum, something really ill-conditioned. And
yeah. So actually, Yushen, do you want to go to the next slide? I think maybe yeah, this is what I mean by it works really well. Like, so I think in the case that if the Hessian was well conditioned, all of these would be pretty much the same. But the fact that the implicit higher order method gave such a big benefit must mean that this problem is ill conditioned, which I think is true because if you actually compute the Hessian of this, it's some complicated function of U and V.
Okay.
And then the U and the V, I think, will cause these ill conditioned issues as they converge to a true solution. But we have to work through the math. Actually, we should probably actually compute the Hessian of this at some point.
Do you mean the Hessian with respect to U and V? Just U. Yeah, that's something non-convex, right?
Yeah, but
it's like xy minus z squared, like xy minus some constant squared, which is
I'm sorry to dominate the conversation. Yeah, I'm sorry to dominate the conversation. So anyone else in the audience should chime up. But can you explain again? Maybe I missed it. Could you explain the plateau in that blue curve?
I don't think we can. This one, I think, because it's a non-convex problem, I don't think we know why it happens. We just aren't surprised it happens.
Yeah, for me, I think I don't see this issue when I redo the experience on my own.
Oh, you don't? Okay, because we use alternating least squares quite a bit in some tensor approximation approaches, and it's an extremely frustrating method, but we see convergence like that. Converges rapidly, stagnates for a long time, and then converges again, stops again. So
yeah, I think alternating
I
think alternating is fine if the function is smooth, but if you are not smooth, then they will get stuck at some strange place.
Convex, you mean, not smooth.
Oh, I mean smooth. Yeah, I think for alternating method, usually fail because of non-smooth point. But for non-convex, I mean, yeah, that's good.
Yeah, Robert, thank you for bringing up all these interesting things that we now know more of what to do on this project.
No, I learned a lot, so I appreciate very much the talk and the discussion. Thank you very much both.
Yeah.
No more questions from anyone? They're probably all looking for lunch at this point, so.
Yeah, the summer is in lunchtime, so yes, everyone's hungry.
And the sunshine's come out here, so now it's time for me to go for a walk. Okay.
Oh, I see.
Go
Because I'm in
quick,
Greenfield.
go
Yeah.
quick. The sun just went out again here, so.
Oh, okay. Okay.
Fog
Well,
is back.
Yushen, I guess one quick last round of applause. So thank you very much indeed. That's good.
Also, thank you so much for the values suggestion. It's very helpful.
No, yeah. Now, next time we're in the office together, just stick your head in. We'll have a chat. I look forward to learning more detail.
Yeah, sounds good. Thanks a lot.
Thanks. Right. Bye-bye.
Bye.
Thanks, everyone.